Okay, so I was asked to talk about dairy sustainability, and that's a broad topic. And so I chose a topic that I think really is at the forefront of sustainability concerns, and that's the impact dairies have on climate. And here I think we have some very interesting new narrative to share. I call the project that I'm about to talk about Rethinking Methane, the path to climate neutrality, because I indeed think that the dairy industry in this country and definitely the dairy industry here in California is well on a path to become climate neutral. And that's, of course, a large concept, a very significant concept. Now, if you want to just go back after I finish my talk at some point and watch a 5-minute video recapturing, that captures everything I'm about to say, go to YouTube and Google Rethinking Methane, and there is a 5-minute short video that really has it all together. So really briefly, 2 slides. The one here on the x-axis shows different regions in the world, and on the y-axis it shows greenhouse gas emissions per unit of fat and protein-corrected milk. What you see here is contrary to what many people think. We are not the country or the region in the world with the highest carbon footprint of milk, but indeed we are the lowest. We have the best carbon footprint per unit of fat and protein-corrected milk. You can see here some developing countries are struggling really to keep their carbon footprint under control. They have bigger fish to fry, so to say. This slide here shows on the x-axis total amount of fat and protein-corrected milk per dairy cow, and on the y-axis it shows the carbon footprint associated with that milk production. And each dot here shows the normalized milk production and related carbon footprint of different countries in the world and dairy production. You see here there are many countries on the left side with a very high carbon footprint, and that's because these cows produce very little milk, and these could be countries like India, many African countries, and so on. The United States is not on this graph. We fell off because we have 23,000 pounds on average, well over 10, 11 tons, and so we are here someplace. The reason why I show this slide is because it's very clear. There's a clear relationship between greenhouse gas emissions on the one hand and milk production on the other hand. It's not surprising to anyone on the call here that we have become way more efficient. Back in 1950, we used to have 25 million dairy cows. Today, we only have 9 million. Today, we have fewer dairy cows in the United States than we have horses, 9.5 million horses. But the reason why I show you this is because we went from 25 million dairy cows to now 9 million. And with this much smaller herd, we are producing 60% more milk. That means that the carbon footprint of a glass of milk has shrunk by 2/3. And that is truly astounding. There are 4 main factors that have allowed us to get there: improved reproduction, improved veterinary care, improved feed efficiency and feed in general. We are feeding more energy-dense diets, and we have improved genetics. And that's, of course, very important to everybody here on the call. These 4 factors have really allowed us to shrink the number of animals to historic levels and produce all the product that is demanded by the population we serve. I now want to talk about methane in particular, okay? It's really important because methane sticks out. It's really the Achilles heel of animal agriculture from an environmental perspective today, because people are warning the public to eat things such as butter because of its carbon footprint, replace alternative or the real deal, the real milk with alternatives that are plant-based and so forth. So how do we quantify methane and other greenhouse gases currently? The main way of doing so is called or referred to as the global warming potential, GWP. That means methane, nitrous oxide, and other greenhouse gases are always compared to CO2, and then the so-called CO2 equivalents are calculated. So if something produces 100 tons of methane, you multiply 100 tons times 28, and you arrive at the CO2 equivalent number. And that's a very typical thing to do, but also one that is, I hope, a thing of the past in the near future. Why? Because methane is different from CO2 and nitrous oxide in other ways than just the global warming potential. One is depicted here, namely The fact that methane is not just produced, as you can see on the left side, by fossil fuel sources, by agricultural waste, by biomass burning, wetlands, and so on. The total emissions of methane globally are 558 teragrams, but methane is also destroyed. There are sinks amounting to 550 teragrams globally. So 560 are produced by sources and 550 are destroyed by sinks. And that means the net is not 560, the net is 10. Still a number we try to get down, but it's important to note that methane is not just produced, but also destroyed. And here the main pathway is really oxidation in the atmosphere. That means there are certain molecules that take the hydrogen away from methane and convert it into CO2. Okay, really important. Methane is different from other greenhouse gases insofar that it's not just produced, but also destroyed. And that happens within a very short time frame. You see here that carbon dioxide and nitrous oxide are both long-lived climate pollutants. Once we put them in the atmosphere, they stay there for a long time. The case of CO2, 1,000 years. So if you drive your car, you burn gasoline, the resulting CO2 stays in the air for 1,000 years. Methane, however, is a short-lived climate pollutant with a lifespan of only 10 years. Only 10 years. Methane, remember, is produced and destroyed. Here's this so-called biogenic or biological carbon cycle. If you ever wondered, CH4 is methane, where that C in the CH4, where it comes from, here is where. Take you back to your high school years. What do plants need to conduct photosynthesis? Well, they need sunlight, they need water, and they need carbon. The carbon they get from the atmosphere during photosynthesis, and that carbon then goes into the plants to produce carbohydrates, such as cellulose or starch. These carbohydrates are ingested by our ruminant animal, let's say a cow, and then a certain proportion of those carbonaceous compounds are belched out, or they're coming off the animal's manure in form of methane, CH4. That methane, though, this carbon contained in this methane from our livestock is not new to the atmosphere. It's recycled carbon that originated in atmospheric CO2, that went through plants and then became methane. As I told you before, methane is then converted during a process called hydroxyl oxidation back into CO2 and water. And that CO2 then goes into the atmospheric pool, and some of that is grabbed by plants again to be used in photosynthesis. So this biological carbon cycle or biogenic carbon cycle is just that, a cyclical event. And as long as we don't grow livestock numbers, as long as we keep them relatively constant, the amount of methane produced and the amount of methane destroyed are in balance. And this is a total change in narrative around the impact of livestock, particularly ruminant livestock, on climate. Here you see how this biogenic carbon cycle on the right side, where you have CO2 going into plants, some of that carbon goes into the soil and becomes sequestered, that's called carbon sequestration. Some of that carbon in the plants is then eaten by animals and belched out again. So that's the biogenic carbon cycle on the right side. And contrast that to what happens when we say, look at fossil fuels and related greenhouse gases. Fossil fuels are things such as oil, coal, and gas on the left side here that were stored in the ground for a very long time. We have unlocked that carbon, we have extracted it, and we are burning it with cars, trucks, trains, planes, ships. And when we burn that fossil fuel, that carbon goes into the atmosphere and is new, additional, mark my words here, new and additional carbon to the atmosphere. It's not recycled, it's new and additional. Whereas on the livestock side, it is recycled carbon, okay? Very different. That's one of the reasons why we should never compare cows versus cars. A totally unfair comparison. Now, something really important here. So how do things such as methane differ from gases such as CO2? That's really the helm of the question. So CO2 is a long-lived climate pollutant. It's referred to as a stock gas, and here's why. Let's imagine you were to drive to work every day of the week from Monday through Friday. On Monday, you drive and you put CO2 into the atmosphere, day one. On Tuesday, you drive again. You put new additional CO2 into the atmosphere, which is now on top of what you put in on Monday, which is still in there, of course, because I told you CO2 is in the atmosphere for 1,000 years. On Wednesday, you add additional new CO2 to the existing stock, and so on. You get the gist of it. Every time you drive a car, you fly a plane, and so on, you add new additional carbon to the atmosphere, to the existing stock, hence the name stock gas. Stock gases accumulate in the atmosphere over time, okay? So is methane also a stock gas? The answer to that is no, methane is not a stock gas. Methane does not accumulate in the atmosphere, but the amount of methane produced, let's say, by 1,000 head dairy, and the amount of methane destroyed is in balance. A flow gas stays stagnant, but and the reason for that is that it is destroyed at the same rate it is emitted. So it takes 10 years, so there's a lag time, but overall methane levels don't go up from, let's say, livestock unless we increase herd sizes. In the United States, in most developed countries, we haven't increased herd sizes in ages. However, that did happen in many developing countries, okay, where herd sizes have grown. In the developed world, our livestock has not increased in size. We have not increased the amount of methane added to the atmosphere, and hence we have not contributed to an additional warming from those livestock herds. If this is the first time you've ever heard that, well, you might want to read up on some of these links that I'm providing here from Oxford Martin, Oxford University in the UK, that were posted by atmospheric scientists with zero background in livestock. The head there is Miles Allen, and you might want to pay attention to what these people have to say. They are clearly saying what we've been doing to methane, which is just converting it into CO2 equivalents, is fundamentally flawed. It does not only not provide any measure of warming, but it is wrong because methane is a flow gas and not a stock gas. It doesn't accumulate in the atmosphere. They have also published well over a dozen papers in high impact factor journals. So I encourage you to really look into this. I give you now 3 scenarios. And genetics really has a lot to do with the solution around methane. 3 scenarios, and then I'll show you how the current way of quantifying methane depicts these 3 scenarios versus a new way that we are proposing. So imagine an increasing amount of methane being released or emitted by the dairy industry, let's say, of 35% over a period of 30 years. The second scenario is a slight decrease of methane over 30 years by 10%. We call it a stable scenario. And the third one is a decreasing amount of methane over 30 years by 35%. If you were to depict the increasing, stable, and decreasing scenario for methane, the way we currently quantify it with a GWP 100, the global warming potential 100, then in all 3 scenarios, the increasing, the stable, and the decreasing scenario, GWP 100 would predict that CO2 equivalent units go up strongly. Even in the case when you decrease methane, the current way of comparing methane to other greenhouse gases would say that even when we decrease methane, we would add additional net greenhouse gases to the atmosphere. However, that's wrong. It is not accurate, and it's now criticized by many in the atmospheric and the climate arena. An alternative to GWP 100 that is proposed is the so-called GWP star. And here is what really happens when you increase, hold stable, or decrease methane. When you increase methane, then we really see a strong warming impact. We do not want to increase methane, period. But if you hold it stable or slightly decrease it, then methane added by our cows does not add additional new warming to the atmosphere. You see here, the blue area is slightly south of the x-axis. That means a slight negative warming. Look what happens when you decrease methane strongly by 35%. In that case, we would have a strong negative warming, which equates to a cooling effect. So what's so different between the GWP 100 that had been used until recently versus the new proposed one is that the old one says every time we put out methane, it has a net impact on warming, when indeed that's not the case. If we reduce methane, we induce cooling. We induce cooling and counteract other greenhouse gases such as nitrous oxide or CO2 from the dairy sector. So the question naturally will be that you will ask, can we possibly decrease methane by something like 35%? And the answer is yes. But before I get there, another quick depiction here. What happens if we increase both CO2 and methane? What happens to warming? If we increase CO2, warming goes up exponentially. If we increase methane, warming for that methane goes up at the same rate. If we hold both CO2 and methane constant, then the warming associated with that CO2 still goes up because it's a stock gas and it accumulates in the atmosphere. However, if we hold methane constant, then the related warming stays constant too. No additional warming from constant cattle herds. But now look what happens when you decrease both CO2 and methane. What happens to warming? If you decrease CO2, you increase warming up until the point where your CO2 is down to zero. At that point, you hold the warming associated with that CO2 constant. But if you decrease methane, you have an instantaneous cooling effect. Instantaneous cooling effect. So again, can this happen? Well, we do a lot of research here on campus at UC Davis in large structures such as those bovine bubbles, with head chambers, with wind tunnels and flux chambers on commercial dairies, with flux towers and so on. And we are quantifying the impacts of how we raise cattle, different breeds, and so on, as well as manure storages. And what we find is that we find strong reductions. In the state of California, we have a 40% reduction goal for methane to be achieved by 2030, and that's a new law. A few years ago, when that law passed, the dairy industry committed to working on that goal, and the state, in exchange, so to say, agreed to incentivize technologies to reduce methane. Put in $1 billion, the state, and work together with the dairy industry, and now we are building covered lagoons and other ways to reducing methane, which have led to a reduction of methane by 2.2 million metric tons per year. Meaning every year, so far we have reduced manure methane in the state of California by 25%. We have reduced manure methane by 25%. That means we are already over halfway at our mitigation goal of 40%. And a reduction of 25% means nothing other than a net cooling effect from this industry, meaning we are well on our path to climate neutrality because these reductions in methane will counteract some of the other emissions of other greenhouse gases, such as nitrous oxide, CO2, and so on. If any of this gets your interest going, I'm on on Twitter here. GHG Guru is my handle. My center, the so-called CLEAR Center here at UC Davis, is also on the web and on Twitter. I write a frequent blog, which is quite popular, and I encourage you to check that one out. And our webpage is active. clear.ucdavis.edu is the address. So with that, I hope that I perked some of your interest, and I really want to tell you, genetics is actually the way, it's the key to further improvements of our carbon footprint. And I think that if we continue to reduce methane the way we have been, we will actually not just be viewed as less of a source, less of a liability around climate, but I think we'll be viewed as a potential solution because we can actually pull carbon out of the atmosphere by reducing methane. With that, I thank you very much for your attention. I'm very happy to entertain questions once we are in the panel. Thank you.